Okay, so part 2 of the section 4.6 deals with end behaviors of algebraic functions and mainly polynomial and rational functions. We can also talk about roots and radical functions. We will see if we can do that later. First, let's talk about just like polynomial functions. Okay, what in the world are polynomials? Poly means many, and nomos means words or terms, so many terms, polynomial functions. Okay, the formal definition of a polynomial function is function f of x. It has coefficients times x to the n, and then the next one, the powers usually are written in a descending order, and it goes down to 1 or 1 a1x, and then the last one is a naught, which is the last coefficient. Okay, so this is called the nth degree polynomial, right? Nth degree this is an nth degree polynomial, assuming that a sub n is not equal to 0. Okay, now assuming also that a sub n is positive. Now, of course, a sub n may not be positive, it could be negative. But for the purposes of this graphing, I will just assume that first a sub n is positive. Then what's going to happen is, again, the end behavior, lots of things could happen somewhere close to the origin, but eventually when x is sufficiently large, the graph is going to go like this and like this if n is even. So if you have x to the 14th or the 16th or the 22nd or a 200th, whatever, the graph is going to go like this eventually, right? This is a good experience or good lesson in life. You know, life has ups and downs, but eventually, sometimes what's most important is what happens when the dust settles. And okay, see the big picture of this. If n is odd, then the function will go like this. And the reason this goes like this is because the limit as x approaches n is still going to be infinity. But if n is odd, okay, like x to the third, and by the way, when x is very, very large, all of these terms really don't matter. Okay, the only thing that matters when x is very large is this, because this part grows faster than any other terms. The leading term is going to grow the most, and thereby making every other term irrelevant when x is very, very large. And so when x is very, very small, see this thing like x to the 5th or x to the 9th, when n is odd, it's going to give you a very negative number, making the function to go down to negative infinity. So that's the end behavior of an odd numbered or odd degree polynomial, right? The graph is upside down, so everything is the other way around if a sub n, the leading coefficient, is negative. Okay, so that's the end behavior, and you should know all of these things for polynomials. Okay, and again, this has to do with the limit at infinity, whether it's positive or negative infinity. All right, number 2, rational functions. Now these are pretty difficult to graph, okay, and all kinds of things happen, right? So by the way, polynomial functions, I should also say, these are nice, right? Nice, very nice. Okay, why? Because the domain, there's no exclusion. Every x is welcome, right? Domain is from negative infinity to positive infinity, and it is differentiable everywhere from negative infinity to positive infinity, meaning it's also continuous, right? And so there's no gaps, no holes, no weird things happening. And it's also very smooth at every single point because the derivative exists at every single point. All right, what is a rational function? Rational function is a function in the form of a polynomial over a polynomial. Now the polynomial could be a constant, like 7 or -1. It could be just x itself, or x squared, or x cubed, or whatever, right? Okay, so here we know what happens to the end behaviors depending on the degrees, right? So maybe I should, yeah, maybe I should do it this way. Part A. Let's say we are looking at a polynomial like 5x squared over 3 divided by 2x cubed minus 1. Okay, now can you tell just by looking at this fraction what happens as x approaches infinity? All right, let's think about this. And I hope you can remember, not just memorize these, the patterns and the rules, but read and try to understand what happens when x is very big. Sorry, when x is 1,000. Okay, so if x is 1,000, that's a pretty big number. 1,000 squared is a million. So you have 5 million minus 3 on the top. When x is 1,000, 1,000 times 1,000 times 1,000 is a billion. This is 2 billion minus 1. So that fraction is very, very small. In fact, it's almost 0, right? And that continues. So when x, see, the point is x cubed outgrows x squared by very, very large numbers. And so what dominates this is the fact that x cubed is in the denominator, making the denominator much larger than the numerator, which means that f of x approaches 0, okay? But there is a way to figure this out. And so let's divide everything by x squared. Okay, you know what's going to happen then? 5x squared divided by x squared minus 3 divided by x squared. 2x cubed divided by x squared minus 1 over x divided by x, 1 divided by x squared. Okay, so that what's going to happen is when you do that, okay, I haven't really changed anything. This becomes 5 minus 3 over x squared. And then this is 2x minus 1 over x squared. But you can see that this approaches 0 and this approaches 0 as x approaches infinity, right? So as x approaches infinity, so let's go ahead and write this down. As x approaches infinity, this approaches 5 over 2x. Notice I didn't put an equal sign because these are not equal to each other. All right, so then this, of course, goes to 0, right? As x approaches infinity, because the denominator gets bigger and bigger. So you can see by dividing each term by x squared, which is not changing the quantity, and since x is a large number and not 0, you can divide everything by a certain same number or quantity like x squared. And you can see that as x approaches infinity, this f of x approaches 0. Okay, and in fact, this happens every single time the denominator has a larger exponent, the degree, than the numerator. So that's the first statement I'm going to say. If the degree of qx is bigger than the degree of px, then there's a horizontal asymptote. Okay, I should say f has a horizontal asymptote, y is equal to 0. Okay, because f of x approaches 0, the limit at infinity and negative infinity are both going to be 0. Okay, all right, so that's the first thing. Now the second example, if f of x is, let's say, 5x squared minus 3 over, did I put 2? Yeah, 2x squared minus 1. So the only difference is I changed this 3 into the 2. Now what's going to happen? Okay, I'm going to do the same thing. I divide the top and the bottom, each term by x squared. So then you get 5x squared over x squared minus 3x over x squared, 2x squared over x squared minus 1 over x squared. That's 5 minus 3 over x squared, 2 minus 1 over x squared, as x approaches infinity, this goes to 0, this goes to 0. And so that as x approaches infinity, this becomes 5/2. Okay, where did 5 and 2 come from? Well, clearly that came from the leading coefficients. And so this gives us the idea if the fact that if Q and P have the same degree, then F has a horizontal asymptote, which is at the level of this, limit as x approaches infinity, or negative infinity for that matter, which is y is the ratio of the leading coefficients of P and Q. Okay, so in this particular example, the horizontal asymptote is y is equal to 5/2. Okay, and the graph is going to get closer and closer to that as x approaches infinity and negative infinity. All right, so what happens when you have something like this, 5x² / 3, and then 2x - 1? Notice here again, I'm using similar examples so you can see exactly what's happening. So first I had the second degree polynomial divided by the third degree polynomial. Then for the second one, I had a second degree divided by a second degree. Now we have second degree divided by a first degree. I can still try to do the same thing. Divide everything by x². Okay, so what is that? It's 5 - 3/x², and then that's 2/x - 1/x². And the point is, this goes to 0, this goes to 0, this goes to 0. Whoops, this denominator is supposed to go to 0, gets closer and closer to 0, but the top is going to stay around 5. That's going to go to infinity, right? So here we have no horizontal asymptotes. And so that's basically the story of horizontal asymptotes. They are closely related to the limits at infinity. Okay. Now I do have a little additional piece of information I should give you here. I didn't tell you everything. Okay. So basically, what this says is if the denominator has a bigger degree, then the horizontal asymptote is going to be 0. If the degrees are the same, look at the ratio of the leading coefficients, and that's going to be your horizontal asymptote. Otherwise, there is no horizontal asymptote. Okay, but here's the question. What if you have this rational expression, rational function, px/qx, each of these is a polynomial, where p has, where the degree of px is exactly 1 more than the degree of qx. Okay, then something else happens. Maybe you already learned how to do this in your pre-calculus class or an algebra class. Okay, let me give you an example, and then you can see. And by the way, the short answer, spoiler, that you will see an oblique asymptote. Okay, well let's see what happens. So here is an example. Okay, this is second degree on the top, and on the bottom is the first degree polynomial, right? So of course the second degree polynomial has 1 degree bigger than the denominator. So how do you analyze a function like this? Well, you can do a long division. It's called long division just because it's called that for in arithmetic, but it's also long division because it's a very long procedure. Okay, it's not so long for this one. I hope you know how to do that. You are dividing what's on the top by what's on the bottom. So 3x², to get 3x², I need to have 3x of these. times x plus 2. That's 3x squared. This times this now is 3x squared plus 6x. And then we do subtracting. Okay, you know how to do that? It's 4x minus 6x, so negative 2x. Okay, and this divided by x plus 2, you put negative 2 here because then you have negative 2x minus 2 times 2, that's 4. And since you are subtracting this from that, it's 0 minus negative 4, and the answer is 4. All this to say, f of x, which is this fraction, is actually 3x minus 2 plus 4, the remainder divided by the original denominator. All right, so this part is actually a line, right? Y is equal to 3x minus 2. This part is a fraction, and as x approaches infinity or negative infinity, 4 over x plus 2. This last part approaches 0. So if this approaches 0, then the entire fraction f of x gets closer and closer to this part, because this whole thing approaches 0. And so that is your oblique asymptote. Because remember, f of x gets closer and closer to this because the last term approaches 0, oblique asymptote. I will abbreviate this as OA. So let's try to graph this, okay? Let me draw the axis. Okay, so a couple of observations. I said f gets closer and closer to this line, so this line serves as an oblique asymptote, all right? We can graph that. Let's go ahead and graph that function, and maybe I should use a dotted line, light green maybe, because see, the oblique asymptote is not a part of the graph, right? And so you go from here, and the slope is 3. And so it looks like it's going to go like that. That wasn't very clear. Maybe I should draw with a little more authority. Okay, so that right here, like that. Okay, so that's the oblique asymptote. Let me label that. Oh, that's not it. Okay. Oblique asymptote, which is y is equal to 3x minus 2, and this point is negative 2. Okay. Also, we are told that, well, we're not told, but if you look at this, as x approaches negative 2, f of x approaches infinity, positive or negative infinity, depending on which way you approach negative 2 from. So at negative 2, what you have is a vertical asymptote. So it's like this. Okay, and in fact, let me just extend this a little more. It's going to be like this. All right. Now, if you plug in 0 for x, you see that the numerator is 0, denominator is 2, so that's 0. So this graph goes through 0, 0. Okay. Now, I didn't do any calculus in the sense that I didn't take the derivatives and so on. So far, everything you learned is calculus free. In other words, you probably learned how to do this in your pre-calculus class. Okay. I have an oblique asymptote, and now this thing, when x is more than negative 2, okay, when x is, as long as x is to the right side of this vertical asymptote, x is equal to negative 2, this thing is positive. 4 divided by a positive number is positive, and as x approaches infinity, this will stay positive, and it approaches 0, right? And so it's going to get closer and closer to the line 3x minus 2, but this is positive, which means the graph is going to stay slightly above this asymptote, like this. Now, we also know that this will have to approach the vertical asymptote, and we know, well, you probably can figure out as x approaches negative 2 from the positive side, so approaching it, like this way to negative 2, this denominator I'm talking about x like negative 1.9, negative 1.99. This will stay positive. The top is also going to be positive, and therefore it's going to approach the positive infinity. Okay, just a little bit of analysis, you can tell this is going to happen like this. Okay, I'm running out of space here, but this other side is going to go like this. So typically, you know, what you do is you do a schematic picture. Like basically what you see is something like this. You have these two asymptotes, and the graph is going to go like this on one side and like this on the other side, right? And we could do all of these just by looking at, you know, this long division and analyzing what the oblique asymptote is. And then other than that, we didn't take first or second derivatives of any of these. And so that's how you can graph these rational functions, all right? Again, rational functions are much more difficult to graph than polynomials, whose end behaviors are pretty obvious and well established. Okay, and the polynomials are much nicer in the sense that the domain is the entire real numbers, entire real number system, and the you know, it's differential and continuous everywhere. There are no asymptotes for these polynomials, but here you may have horizontal, vertical, and or oblique asymptotes. We are going to be sketching a few more graphs, but let's just add a couple of notes, all right? I want you to imagine and try to figure this out. What is the limit of the sine function as x approaches positive or negative infinity? Okay, well, you can see it's going up and down like this. So this does not exist. There is no limit of the sine function at infinity or at negative infinity. And how about the tangent function? Oh, by the way, the cosine is the same thing. Okay, the cosine function, because it goes up and down, this does not exist, and neither does the limit as x approaches negative infinity. All right, tangent function, it goes like this. Again, it goes really up from positive to negative to positive infinity, and then coming back from negative infinity to positive infinity. So the limits at the infinity do not exist. You know, again, as x approaches infinity or negative infinity, the limit does not exist for these periodic functions. Now, e to the x is a different kind of thing. So this is infinite, right? Because you know the graph actually approaches infinity. And in fact, it is exponential growth. I mean, literally, this grows exponentially. So this is that. But as x approaches negative infinity, e to the x, so that is the graph that goes this way, gets closer and closer to 0. So you do have an horizontal asymptote at y is equal to 0, otherwise known as the x-axis, because as the graph goes to the left, it approaches 0. And remember what an asymptote is. It's a line that gets closer and closer to the graph, so that the distance between those two approaches 0 as the points go away from the origin. And that's exactly what's happening. All right, so you know that there are all kinds of functions. We have just scratched the surface. We have just done a couple of polynomial functions and maybe 1 or 2 rational functions. There are many other functions, and including now things like the asymptotes, the 3 types of asymptotes, and the first and the second derivative test. We can gather a lot of information, and that is going to help us graph functions. So in the last section of subsection of section 4.6, I am going to give you a couple of additional functions to graph, and then we will graph together along with, you know, finding out what we can find. We can establish by looking at its first and second derivatives.